So we're given here a non-homogeneous linear differential equation with constant coefficients. And so this means that a good method for finding a particular solution is undetermined coefficients. So if we use undetermined coefficients, the way that we do that is by guessing what should a particular solution be. So a general particular solution with undetermined coefficients. And this guess that we make for yp is always determined by this function on the right-hand side of the equation. So we ask the question, what does a general linear combination of this function here and its derivatives look like? And in this case, that's quite obvious. It's just going to be a e to the x. Good. So when we substitute this back in, this would be the technique. So just following undetermined coefficients, we have to substitute this guess back into our equation. Here, we're just going to get, so that every derivative of this function is just equal to itself. So when I substitute this back in, I'm just going to get a e to the x minus a e to the x, and this is equal to 0. And that's a bit of a problem here, because this is not telling us anything about what the value of a should be, because a can be any value, and we're always going to get 0. Okay, so here you see where the method of undetermined coefficients really breaks down. And let's try and understand why this broke down. So the reason why this whole method broke down is that if we look at this differential equation here, its complementary function, the general solution to the homogeneous equation here, associated homogeneous equation here, is just going to be c1 times e to the x plus c2 times e to the negative x. And the issue here is just that the particular solution, our choice of particular solution here, is already a solution. It's already part of the complementary function. So that no matter what this value of a is, we're always going to get 0. And so we can never determine this coefficient a. All right, so how to overcome this issue? So the way to overcome this is by updating our choice here. So by looking at this complementary function, what we're going to do is change our guess here. We're going to change our guess of yp, update it, and we're going to update it in a very canonical way, which is to just multiply this function here by x. So we multiplied by x, and now the general issue that we saw earlier, that our yp was a solution to the homogeneous equation, no longer exists. This function here is no ways can be obtained by choosing constants c1 and c2. Okay, so this is our new guess. Now let's see if we try the method. So we plug this function back into our differential equation here. We're just going to get so the second derivative of this function you can check is going to be a times x plus 2e to the x, and then minus our function, which is just a x e to the x. So this cancels out nicely, and we're just going to end up with 2a e to the x. All right, this is good. So we're not getting 0, and so we can just argue as we usually would. We have to argue that this has to be equal to, of course, it has to be equal to the right-hand side of this function. If it's a particular solution, it must be equal to this. So we must have that this is equal to e to the x, and this forces this coefficient to be given by just a equal to a half. Great. So that means a particular solution here can be found, and that's equal to just half x e to the x. Which is very good news, because then we can solve the general solution here. The general solution to our equation is just the complementary function plus the particular solution, as it usually is. Okay, so let's try and formulate now a general method for finding particular solutions using undetermined coefficients. So here is our recipe. So we're going to update our method of undetermined coefficients. So we start off with a general linear differential equation here. And the first thing that we're going to do is compute the general solution to the associated homogeneous equation. So to compute the complementary function here. Okay, so once we have that, then we're going to, as usual, make a guess as to what is the general shape. So we're going to make a guess yp, which is supposed to represent a general linear combination of this function g and its derivatives. Okay, good. Then the issue that can happen earlier, it can appear here. We can have that certain terms here match. So certain of these functions, y sub p1 for instance, could be a solution to the associated homogeneous equation. It could appear here. And that's a bit of an issue. That's a problem. It's really the same problem here, right? The problem here was that our function a e to the x was already a solution. It was matching with the complementary function. So our goal is to eliminate such matching, and the way that we're going to do that is by multiplying by the smallest power of t here, which eliminates this kind of matching. So we multiply by x to the t, where t is the smallest integer, such that two things happen. Firstly, x to the t times yp to the k is no longer a solution to the homogeneous equation. So then we've eliminated that problem. But then also we would just want that the x to the t y sub pk together with the rest of the functions is linearly independent. It could happen, for instance, that you multiply by x and get one of the other functions. So you just want to then continue multiplying until these two conditions are met. Okay, great. So once you've achieved that, then you're in a position to just substitute the yp back into the equation here, equate the coefficients of that function yp with g of x, and find the coefficients, and then you have your general solution here. Okay, good. So let's, this is a long technique, so let's illustrate it immediately on an example. We're asked to solve this differential equation here. So we're going to follow the steps that we just described. So the first thing we need to do, according to our method here, is find the general solution of the associated homogeneous equation here. Okay. Now the associated homogeneous equation in this specific case is just, it's always just set the right-hand side equal to 0. So this is equal to 0. Now solving such problems has already been addressed many times. This is a linear differential equation which is homogeneous and has constant coefficients. So there's a very nice way to solve it. You associate to it the auxiliary equation, and you get this. And so this immediately gives you three roots, sorry. It gives you r is equal to 0, or r is equal to 1, or r is equal to -1. And then we just have to keep track of multiplicities. This here has multiplicity 2 because of the r squared term. And then this decomposes into r plus 1 times r minus 1. And so these are just roots of multiplicity 1. There's no powers here. So these ones are multiplicity 1 and multiplicity 1. Great. So from these roots, we can immediately say what the complementary function is. The complementary function is just going to be given by, so since this is a root of multiplicity 2, we're just going to have C1, so e to the 0x times the general constant, but that's just going to be C1, plus x times e to the 0x, which is just going to be C2 times x. So that's this linear term is just coming from this here. And then these two values of r are equal to 1 and r equal to -1 give us solutions e to the rx respectively. And so the general solution is just going to be C3 e to the x plus C4 e to the -x. Okay, great. So that's our complementary function. Now, second step, we have to guess a general form for our particular solution, which is based on asking the question, what is a general linear combination of g and its derivatives? So if we do that, we take here yp, we ask ourselves, we have to look at this function here, and we have to ask, what kind of functions can I obtain from differentiating this function multiple times and then combining that and adding it to other derivatives of this function. And instead of computing derivatives, let's just argue like this. This linear term here is going to contribute a general linear term. If I take 4x, I multiply it by a constant, and I add that to the derivative of 4x times another constant, I just get a general linear function that looks like this. Okay, next, the function here, which is 2x e to the negative x, we can, if we differentiate x e to the negative x, I'm going to get just e to the negative x plus x e to the negative x. So that this term here is contributing two different terms, two different functions. And so what we're going to do is have a general linear combination of them, which is going to be c e to the negative x plus dx e to the negative x here. Okay. Okay, great. So that's our guess here. Okay. So we guessed this function here. Good. Now we have to check something. We have to be very careful now. We have to first write down our function. What we're going to do is just find these y sub p1. So for instance, this here is going to be y sub p1, and this one here is just going to be y sub p2. And we're going to check, do these functions match with the complementary function? In other words, for picking a and b here, do they match with the complementary function? In other words, are they individually a solution to the homogeneous equation here? In this case, yes, both of them are. Y sub p1 can be obtained here, and this function here contains a term which is in the which is a solution, namely this one here. Okay, so great. We have to then update our guess here. We have to multiply this function by the smallest power of x, such that something happens, such that no term of it is a solution to our associated homogeneous equation. Okay, so doing that, we're going to get here, if we multiply it by x, let's just compute here. If I multiply it by x, I'm going to get ax plus bx squared. And now I need to ask, this updated function now, does it have a term which is still a solution to the associated homogeneous equation? Answer is yes. The answer is yes. Because and what is that term? It's a x times a, because that can be obtained right over here. Great. So we need to actually multiply by another power of x, another x here, and then we're going to get x squared a plus x cubed b. And you see here, none of these terms here have a term which is a solution to the associated homogeneous equation, which none of these terms can be formed here. Good, so that deals with that, great. The next thing here is also, we have a term which is appearing in the homogeneous equation here, it's this one. Because this one here duplicates with this here. So, what we need to do here is now just multiply by x. And just doing one round of multiplication with x will allow us to solve the problem. So we're going to get here just x c e, so let me write it like this, cx e to the negative x plus dx squared e to the negative x. Great. So that's our new trial solution here. And so that's how we're going to guess the shape of yp. Okay, good. So this is our new guess here, okay? Good. So we've now have our guess, and we're in a position to just substitute it into our equation. So we substitute this value of yp into this equation here. So we need to actually compute we need to compute the derivatives here, and there's 4 derivatives to compute, and this function is big. It's a very big function. So luckily I've done the work here, so I'm just going to write down what these derivatives are. So this here is, of course, the 0th derivative. The first derivative, yp prime, is just going to be 2a x. Of course, you could have guessed that, 3x squared b. And now here, you can just compute the derivative yourself and then group terms accordingly. But you should get c 1 minus x e to the negative x plus, and this continues here. And again, if you differentiate the x squared multiplied by e to the x, then differentiate the negative e to the x multiplied by x squared, and then factor out the e to the x, you just get 2x minus x squared e to the negative x. And this continues. Second derivative here will just be 2a plus 6xb. That again, you could probably guess. C times x minus 2 e to the negative x. And now d times, and now this would have been a little bit more complicated to differentiate, but again, you'll just get a quadratic function, so it should be x squared minus 4x plus 2 e to the negative x. And we continue here, third derivative. And here the constant falls away, so we just end up with 6b because of the x here falls away. So 6b plus c times 3 minus x e to the negative x plus d times negative x squared plus 6x minus 6 e to the negative x. And lastly, we have here the fourth derivative, which becomes fourth derivative here will just be, okay, so now the last constant falls away, so we get c x minus 4 e to the negative x plus dx squared minus 8x plus 12 e to the negative x here. And now we're in a position we've computed all the derivatives, so we can substitute it immediately back into our equation here. So that's exactly what we're going to do. So we need to compute in terms of these coefficients what is yp quadruple prime minus yp double prime. So in this case, we're going to have c x minus 4 e to the negative x plus d x squared minus 8x plus 12 e to the negative x. So that's just the fourth derivative here. And we want to subtract from that the second derivative. So subtracting the second derivative here will just give us a negative 2a. Negative 2a minus 6b, so I'm just subtracting the second derivative here. So minus 6b x minus c x minus 2e to the negative x minus d x squared minus 4x plus 2 e to the negative x. Okay, so what does this end up being? This ends up just being equal to the linear term is going to stay the same, so we're going to have negative 2a minus 6b, and now we can do some cancellations with the c here. So the nice thing is that the x's will cancel here, and we just have a negative 2c. So this term subtracted from this one is just going to give us negative 2c, but then also there's an x here. Okay, an 8x here, which is subtracting from this one here. So sorry, not the 8x, the 12 I mean. So then we have the lone 12 here, and this 10, and the d. And so all in all, if you, okay, let me just say it, if you simplify everything and write it out, you should get a term like this. 10d minus 2c e to the negative x, and then finally minus 4dx e to the negative x. Okay, so I've just written these things down. I didn't do it in my head, so please do check this yourself. You should get what's written here. But the general point is that now we know what this should be equal to. This is supposed to be our particular solution, so it has to be equal to this up here. We have to get 4x plus 2x e to the negative x. So this, we must get 4x here somehow, plus 2x e to the negative x. And this, the point of doing this is that this will give us a linear system of equations. So there is no constant on the right-hand side here, but there's a constant here. And by the way, there should be an x here. Sorry about that. So there's no constant here, and in fact, so that means that the 2a here needs to be 0. So we get negative 2a should be equal to 0. We get the negative 6b should be 4. So we get negative 6b here is equal to 4. And then we get 10d minus 2c, sorry. It's just this coefficient. Should be equal to, well, there isn't such a term on the right-hand side. This should be equal to 0. And finally, the leading coefficient here, negative 4d, should be equal to 2. So we get negative 4d equal to 2. And we can solve the system. Of course, this means a is equal to 0. It means b is equal to 4 over negative 6, which is negative 2 over 3. And then d here is just equal to negative a half. And then finally c, if we know what d is, then 10d will be negative 5 here. And then bringing that negative 5 over and dividing by the negative 2 just gives us negative 5 over 2. Excellent. So that gives us a particular solution. Our particular solution then, if you remember, is just going to be ax squared plus bx cubed plus c. Let's just go back up and check. This was our choice here. So plus cx plus dx squared, all multiplied by e to the x. So plus cx e to the negative x plus dx squared e to the negative x. Great. So we have the coefficients, and finally we immediately get then that since the a is 0 and the b is negative 2 over 3, we just get negative 2 over 3 x cubed here, minus 5 over 2 x e to the negative x minus a half x squared e to the negative x. And so that's our particular solution. So that's the particular solution, which means that the general solution to our equation, which is just the complementary function plus the particular solution here, is just going to be equal to, so if we just find what is our complementary function, it's this one up here. So I just copy it. So it's just that plus this. Great. Just to make them the same color, here we are. So this is our final solution. So you see, these things kind of get long and complicated, but the important thing is that the method that we use is uniform. Okay, thank you.